Hello and welcome to my Physics Lab 3 presentation. In this lab, we create a simulation of a star's motion around a black hole with unknown mass. With randomly generated trajectories and our knowledge of fundamental physics principles, we estimate the net force acting on the star and use that information to determine if we are able to estimate the mass of the black hole. At the end of the lab, an average was taken from resulting data points to make an approximation for the mass of the black hole. Before diving into the code, we should first review the needed fundamental principles. With the trajectories generated, approximate velocities were calculated using final position minus initial position all over delta t. With this information, we use Newton's second law to determine the net force acting on the star. The net force is equivalent to dp over dt, which is approximately the same as delta p over delta t for a relatively small delta t. Momentum is also defined as mass times velocity, which can be used to derive the change in momentum formula. F net can also be considered as the sum of the net forces on the parallel and perpendicular direction. F net parallel determines the magnitude of the net force, while F net perpendicular determines the change in direction of the net force. Since the black hole will be exerting a gravitational force on the star, we also need the universal gravitation formula. The given information from the lab instructions were plugged into the corresponding variables in the Glowscript simulation. Gravitational constant is needed as we are assuming that the net force on the star is solely due to the black hole. Delta t was set to 86,400 because the time between the trajectories are thought to be 1 day, which was converted into seconds per SI units. We finally use our knowledge of fundamental principles to fill in the missing information based on the data given. The F-net variables were set equivalent to its respective dp dt variables, since F-net equals dp dt as stated from Newton's second law. For dp dt perpendicular or F-net perpendicular, there is no way to properly determine the radius of the star's orbit around the black hole. Therefore, we have to use F-net minus F-net parallel, since the two components make up F-net. This set of code is encapsulated within a while loop, as each iteration accounts for each velocity taken from the generated trajectories. These were the final magnitudes for net force and each of its components. To estimate the mass of the black hole, I used what we know about the relation between F-net and the gravitational force of the black hole. Since we assumed that the net force on the star was solely due to the black hole, I set the magnitudes equal to each other and solved for the mass of the black hole. The resulting equation can be seen in the code. Since the star's position changes in the while loop, we get numerous estimations of the mass, but we make the best approximation by averaging out all of the masses gathered from the iterations, which led to the mass of the black hole being approximately 1.69 times 10 to the 16th kilograms. This simulates the star's motion around the black hole. The orange arrow represents F-net perpendicular, which points to the kissing circle. The blue arrow represents net force, and the purple arrow represents F-net parallel. In most cases, net force and the rate of change of momentum have equal value. However, they are not necessarily the same. In calculating net force, we used dp over dt, which was determined using the formula p equals mass times velocity, which is used in non-relativistic contexts. But when the object's motion is close to the speed of light, p should equal gamma times mass times velocity, which we did not account for in this lab. Furthermore, conceptually, the net force exerted on the object is the cause for the changes in momentum. So they have the same value, but they represent different concepts. If the current black hole was replaced with a new black hole, it would be impossible to calculate a different mass for the new black hole, as the values in our code would not change with the different black hole. The black hole exerts a gravitational force on the star, which affects the star's motion. However, in this lab, the star's motion was predetermined from the generated trajectories, therefore nothing would change. The star's motion would have to change in some way in order to have a new mass for the black hole.